So we're going to start a new chapter. We're going to be talking about square roots and cube roots and perfect squares and perfect cubes and Pythagorean theorem. That's basically what the whole chapter is about. So today we're starting with perfect squares and square roots. So I have a question for you. I want you to draw a square, but that square needs to have 4 little squares in it. Is that possible? Could you draw on this grid here a square that has 4 little squares? You see there's 1, 2, 3, 4, 5. There's all these little squares, right? Make a square that has 4 little ones. Well, it shouldn't be too bad if I do something like this. There you go. There's a square and it has 4 of them inside of it. Alright, what's another number I could do it with? How about 9? Could you make a square that has 9 of them? Sure you could. You could do like this and like this, and sure enough you have 9 little squares inside of it. Sorry, I kind of messed up there, but you got 9 of them in there. Can you think of other numbers like that? How about 25? Could you do it with that? Absolutely. Something like this, like that, and there's 25. Well, again, I'm sorry, but there's 25. 1, 2, 3, 4, 5. And there's 1, 2, 3, 4, 5 this way. 5 times 5 is 25. Okay, look what we did. When we did 4, what was the square like? It was a 2 by 2, and 2 times 2 is 4. When we did 9, it was a 3 by 3, right? 1, 2, 3, 1, 2, 3. 3 times 3 is 9. And we did 25, it was a 5 this way and 5 this way. 5 times 5 is 25. Hey, I missed the 4 by 4. What was that? 16 would have also worked, wouldn't it? 16 would work. I could go 4 down, 4 across, 1, 2, 3, 4, and it makes a perfect square. It makes a perfect square. And these numbers over here, 4, 9, 16, 25, these are all perfect squares. The reason they're perfect squares is you can make squares out of them. Now, not every number is a perfect square. What if I had a number like 5? There's no way to make a square with just 5 unless you go a little bit over, right? It would have to be something like a little bit over. It just gets so ugly. It's like, oh, I don't know. I have 1, 2, 3, 4, and if I add together these little bits here, 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 and here, I guess it adds up to a 5th. But that's really, complicated and ugly and everything. We like these ones. These are our perfect squares. So, with that background, I'm going to start defining a few things. The first thing is squaring a number. So remember, let's say I drew a big square here, and I said, how many squares, little squares, are inside that square? Chances are you wouldn't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I mean, you could, but another way you could do is you could just count across the top. 1, 2, 3, 4, 5, 6, 7. There's 7 across here. And 1, 2, 3, 4, 5, 6, 7. There's 7 down here. And you could figure out the total amount by going 7 times 7. And that equals 49. There's 49 of them in here. Another way you could do 7 times 7 is you could square the number. Squaring a number means multiplying a number by itself. And I guess the reason it's called squaring is because if I took a certain side length, like let's say I took a side length of 6, 1, 2, 3, 4, 5, 6. If I wanted to square that number, this is 6 right here. If I wanted to square that number, it means I'd put another 6 over this way. 1, 2, 3, 4, 5, 6. So I'd have 6 times 6. We're going to end up with 36 squares in here, aren't we? Yes, we are. When I close up this, I've now squared the number effectively. I get 36. So squaring a number is just multiplying a number by itself. We can also say, instead of saying squaring a number, you can also say we raise the number to the second power. So this right here is 5 squared, or you can say 5 to the second power. 8 squared, or 8 to the second power. 1 squared, or 1 to the second power. Okay, I got to give you just a little bit of lingo here. So I'm going to write this as 5 squared. I'm also going to write it up here. Okay, so each of these numbers have a name. The big number, the 5, the 8, the 1, that number is called the base. Big base. Okay, BB, big base. The small number up here, the 2, that's called the exponent, or you can also call it the power. That's why we're allowed to say 5 to the power of 2 or 5 to the second power. But often if it's just 2, we just say 5 squared. It's the easiest way to say it. And again, the reason we say squared, because you can literally make a square on a grid like this when you multiply a number by itself. Alright, so let's try some of these. 5 squared. Now, a common answer people put down for that is 10. They go 5 times 2. This does not mean 5 times 2. Remember, it means multiply a number by itself, and I think I'm even going to put in brackets here, 2 times. Multiply it by itself 2 times. That's why it has that 2 there. It tells you do it 2 times. Guess what you'd do if it had a 3 there? You'd multiply by itself 3 times, and we're going to do that later in this chapter. Okay, but for this one, we're just doing 5 times 5. That's what 5 squared means. Now, it's not the answer. The answer is 25, because 5 times 5 is 25. 8 squared does not mean 8 times 2. It means 8 times itself 2 times. 8 times 8, which is 64. 1 squared means 1 times itself, not times 2, but by itself 2 times. So 1 times 1, which equals 1. Okay, now square root. Square root is just the opposite. So that would be like if you start with the 25 and you go back to the 5. What you're doing basically is finding the number that has been squared. So for example, if I wanted to know what the square root of 25 is, I'm asking you, what's the number that got squared to get 25? Oh, well the number that got squared to get 25 was 5. Not 5 squared, but just 5. What was the number that we squared to get 64? We squared 8. So the square root of 64 is 8. So the question you're kind of asking is, what number was multiplied by itself to get whatever square you're looking for? So in this case, what number was multiplied by itself to get 9? What number was multiplied by itself to give 49? What number was multiplied by itself to give 100? And as you can see in all these, for square root, we denote it, or we show it, with a symbol that looks like this. That is the square root sign, also called the radical sign. Now, some numbers are perfect squares. We already talked about them. Perfect squares are numbers like 4 and 9 and 25 and 16 and 49 and 36, right? These are all perfect squares because you can form an actual square with them when you put it on the grid. 5 is not a perfect square. Remember, it was so ugly when we tried to make that one. So it's a number whose square root is a whole number, not a decimal. So here's some examples down here. We actually talked about some of them already. Square root of 9. So what you're asking yourself with this is, what number do you multiply by itself in order to get 9? So the same number has to go in here and here. What number would go in there? Well, it would be a 3 and a 3, wouldn't it? So our answer is 3. In this case, we're asking, what number is multiplied by itself to give 49? Has to be the same number. What has to go in there? It must be 7 and 7. Oh, so the answer is 7. You multiply 7 by itself to get 49. This one, square root of 100, you're asking what number times itself equals 100. You don't have to write this down, right? I'm just doing this to help you understand. You can put the answer right away. Now, I don't know why, but when we have this question, square root of 100, people start thinking about 50 and 2. That's not the same number. It has to be the same number here. But if it was 10 and 10, oh yeah, that works. 10 times 10 is 100. So the square root of 100 is 10. So let's take a second at the bottom of the page, write down the first, 15 perfect squares. So I'll get us started. 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square. How come? Why are these all perfect squares? Because 1 times 1 equals 1, 2 times 2 equals 4, 3 times 3 equals 9, 4 times 4 equals 16. How do I get the next one? 5 times 5, 25, 6 times 6, 36, 7 times 7, 49, 8 times 8, 64, 9 times 9, 81, 10 times 10, 100. Why am I'm having to squish more and more? It's embarrassing. 11 times 11, 121. 12 times 12, 144. 13 times 13, 169. If you get up to there, I'm pretty happy. 14 times 14, 196. And if you can get all the way to 15, that'd be great. 15 times 15, 225. Now, does it stop there? Of course not. 16 times 16, 256. 17 times 17, 289. 18 times 8, right, just keeps going on forever. There's infinite numbers of them. But these are all perfect squares. There's actually one more way back here. What can we also put? 0. 0 times 0 is 0. Okay, so there's the list of the first, 16 perfect squares for you. Sorry it's so sloppy. Alright, let's do a few more complicated things. First of all, fractions, right? We're going to square some fractions. We're going to take the square root of some fractions. Looks scary, right? It's not. You know why? You just square the numerator, and square the denominator. So if you have 2/3 squared, the whole thing squared, basically all you do is square the numerator, 2 squared, and square the denominator, 3 squared. So what does 2 squared mean? It means 2 times 2. And what does 3 squared mean? It means 3 times 3. And now we can finally get our answer. 2 times 2 is 4, and 3 times 3 is 9. Of course, once you've done a few, you don't need to write all this out. You could just put the answer, like that. Now, there is another way you could think of this. 2/3 squared means 2/3 multiplied by itself 2 times, right? Where the base is 2/3 in this case, and the power, or the exponent, is 2. So we're multiplying the base by itself 2 times. 2/3 times 2/3. Now, you know how to multiply. You don't need common denominators, even though we have them here. You just ninja slice if you can, but you can't. And then multiply across the top. 2 times 2 is 4. And multiply across the bottom. 3 times 3 is 9. You're done. You have a choice with these ones. You can either go 5 over 4 times 5 over 4 and get the answer that way. Or you can go 5 squared over 4 squared. What's 5 squared? That means 5 times 5, which is 25. What's 4 squared? 4 times 4, which is 16. And you're done. Yeah, you can make it 1 and 9/16, but this is fine too. Okay, what do you think about this one? Well, what I would suggest is, since we're basically going to be multiplying, aren't we? We better switch this into improper. Whenever you multiply fractions, you got to put it improper. So 2 times 2 is 4, plus 1 is 5, and the denominator stays the same, and we are squaring it. So again, you can do 5 over 2 times 5 over 2 and get the answer that way, if that's easiest for you. Or you can go 5 squared over 2 squared and get the answer that way. That'll also work. 5 squared, that means 5 times 5, which is 25. 2 squared, that means 2 times 2, which is 4. And that's fine. Make it 6 1/4 if you want. Now, how about this? Now we're taking the square root. Well, it's kind of the same. If you're taking the square root of the fraction, take the square root of the numerator and the square root of the denominator. So, in the first one, the square root of 9 over 121 is the same as the square root of 9 over the square root of 121. Now you just need to remember what square root means. It means, what number do you multiply by itself to get 9, right? A number times another number, and it equals 9. Well, that's 3 times 3, so square root of 9 is 3. Don't put the square root sign again. Oftentimes people do that, put the square root sign again. No, you took the square root, and we're left with 3. Square root of 121. What number times itself equals 121? It's a bit of a tougher one. It's 11 times 11. So we get 3 over 11 as our answer. Okay, how about this? We can do the square root of 12 and the square root of 75. But wait a minute. Square root of 12, that's not a perfect square, is it? What number times itself equals 12? There's nothing that multiplies by itself to get 12 except some crazy decimal. Oh no, how are we going to do this? Well, you know what you should do before you give up? Always put your fractions in lowest terms before you give up. So, 12 and 75, do you know what you can divide them both by? You can divide both those things by 3. We're going to divide by 3 and divide by 3. 12 divided by 3 is 4. And 75 divided by 3 is 25. Ooh, look at those numbers. They might not look special to you now, but by the end of this chapter, you'll look at numbers like that and be like, oh boy, oh boy, oh boy, this is great. These are perfect squares. I can do this. So I take the square root of the top one and the square root of the bottom one. What's the square root of 4? What number multiplies by itself to give 4? 2 and 2. So the top number is 2. What number multiplies by itself to give 25? That's 5 times 5. So it's 5. Our answer is 2 over 5. Okay, last one here. 2 1/4. I bet you can guess what you're going to do. You're going to switch that into improper. 2 times 4 is 8, plus 1 is 9 over 4. And whenever you take the square root of a fraction, you can just take the square root of the top and the square root of the bottom. What number multiplies by itself to get 9? Oh, we did it over here. 3 times 3 equals 9. So the square root of 9 is 3. And what number multiplies by itself to give 4? A number multiplied by itself gives 4. 2 times 2 equals 4. So our bottom number is 2. You can leave it like that, or of course you can make it 1.5. Either way works. Okay, last thing. Inverse operations. Inverse operations are operations that undo each other. They kind of reverse the effect of one another. So an easy example is add and subtract. If I take some amount let's say 5 is my starting number, and I add 3, and then I subtract 3, where do I end up? Well, I end up at 5. Adding 3 and subtracting 3 just kind of undo each other. It's like nothing happened, so I end up where I started. Another example is multiply, divide. Let's start at 5 again, and let's say I multiply by 2, and then divide by 2. Where do I end up? Well, 5 times 2 is 10, divide by 2 is 5. I'm back here again. How come? Because multiply by 2, divide by 2 are inverse operations. They just undo each other. It's like nothing was ever done. Well, the two things you learned today are inverse operations, square and square root. So let's say I started with 4. I took the square root of 4, and then I square it after that. So first of all, we take the square root of 4. Square root of 4 is 2, because what number multiplies by itself to give 4? It's 2. I think we just did that just above right here, right? So you get 2 as your answer. And now what I'm saying is if you square it, that means 2 times 2, you get 4. We're back where we started. We started with 4. Okay, so they undo each other. So questions like this look really complicated, but that once you get the hang of it, they're dead easy. So in this one, you have the square root of something squared. So the first thing you would do in this case is you would square the inside. 6 squared. What's 6 squared? Well, that means 6 times 6. What the heck, I'll write it in there. Square root of 6 times 6. 6 times 6 is 36. Okay, we did the squaring part. Now let's do the square root. What number multiplies by itself to get 36? 6 multiplies by itself to give 36. See what happens? We started with 6 right here. We squared it and then kind of unsquared it if you want. Square root's like unsquaring. It just undoes each other. So it's kind of no point in doing all this work. If you spot this, just go ahead and write this. Okay, now this time we're going to do the opposite. We're going to do square root first and then square it. So what's the square root of 25? What number multiplies by itself to get 25? 5. Good. Now let's square it. Well, 5 squared means 5 times 5, and that is 25. It happened again. If we square root and square, they undo each other, and so there's really no point in doing all this work. So do you have a hang of it? Here's 87. We're going to take the square root of that. I don't even know what that is. That's not a perfect square. I don't know, 9 point something or other, some big decimal. But what I do know is if I take the square root and then square it, they undo each other, so the answer must be 87. And if you got that, you can do these last questions in mere seconds. 59 squared, well, that's some massive amount. I don't know what it is. But what I do know is when I take the square root of that massive amount, it's going to go all the way back down to 59. Square and square root undo each other. There's a square root, they undo each other. I'm left with 145.7. Square root, square, they undo each other, and we're left with just the base, which is 11 over 13. So watch out for that. Inverse operations undo each other, and you're just left with a starting number. Okay, everyone, there's a fairly long, opening video for this chapter. Hope it makes sense, and as always, let me know when you need help. Bye.